All right, so yeah, I wanted to start off with kind of a rapid fire content review, so we're really comfortable with electrochemical voltaic cells. And I think anything that I ask up here is fair game for your quiz tomorrow. So at any point, if one of you guys is not super certain about one of these things, please raise your hand and I can hopefully go over it a bit more in depth. But I would love it if you guys could kind of like call out the answer for some of these. So actually, the first one is a bad example. You can't really call it out. But what is the purpose of a salt bridge in a voltaic cell? Does anyone want to raise their hand? Yeah. Yep. So I started off with a bit of a trickier one. I'll kind of draw uh, voltaic cell here, right? We know we got the anode, electrons flow with the wire over to the cathode, and then this thing in the middle is the salt bridge, and that has an inert gas on it, or inert solid, I think actually. And inert means that it doesn't react. So it's a non-reactive salt that's going to go to separate sides. And I think I might be getting ahead of myself a little bit here, but you basically are going to have different ions go to different sides of the voltaic cell to keep it electrically neutral. So in one word, the answer to this is electroneutrality. All right, next one. Which electrode is the site of oxidation in a voltaic cell? Anode. Yep. So as a review, I like this acronym or this way of remembering anode, oxidation. These are both vowels. Cathode, reduction. These are both consonants. Once I learned that, I never forgot this again. All right, and that's the answer to the next one as well. In a voltaic cell, which electrode is positively charged? This one's a bit trickier. Cathode. Yep, it's cathode. So in this case, we have the cathode. There's ions. If we think about a standard electric cell, it kind of has ions going towards the electrode. So we could draw an arrow going from the solution towards the electrode. Whereas on the anode, so I should probably label these, the arrow is going to be going off of the electrode because we're dumping ions into the solution. So, yeah, does that make sense? Next one. Do electrons flow from anode to cathode or cathode to anode? Anode to cathode. Yep. So we almost always see this written where the anode is the thing on the left, the cathode is the thing on the right. So we can kind of draw electrons flowing through this wire to the right side. And again, that should make sense because if we're oxidizing over here, that means we're giving up electrons that then can flow over and go to the cathode to be reduced. Um, this next one was kind of not a great one. We can skip it. It's asking why is a spontaneous redox reaction required in a voltaic cell? The answer is that it provides like external energy to a power circuit. That's a little bit too complicated. I don't think you need to know something like that. Next one. What flows through the salt bridge to maintain electrical neutrality? Again, we already said that's ions. So ions are going to be flowing through that thing. Um, we already talked about this one as well. What is the function of the external wire? It's basically to allow electrons to travel from anode to cathode. Um, why do cations migrate towards the cathode? This is a good one. Does anyone want to give a guess why cations migrate towards the cathode? And again, this is talking about with the salt bridge. So if we have the cathode where we have these positive ions, say we had like copper 2 plus being plated onto the electrode to form copper solid, in place of where there were those positive ions is now a deficit. So there's no more positive ions there, meaning we need positive ions from this guy to shoot over here to keep it neutral. Does that make sense to everyone? And so then the opposite can be said over here, where if we're dumping a whole lot of positive ions into the solution, we need anions to go to the side of the anode because that's going to balance out the positive ions being put into solution. That was the trickiest part for me, I think, with these is understanding that. But the cathode, cations, anode, anions, that's pretty easy to memorize. So if you don't want to get super conceptual with it, you can also think about it that way. Um, Kind of building off of what we were talking there, which half cell, so which electrode or which like side of this voltaic cell gains mass during the process? Cathode. Yep. If nothing else, look at the arrows. We see this arrow is pumping more solids onto the cathode. So as this voltaic cell goes through its process, we're going to be adding more solid to that electrode, meaning it's going to gain mass. And then the next one, obvious, the thing that loses mass is going to be the anode because again, we're dumping anions off, sorry, we're dumping positive ions off of the anode into solution. Do we feel pretty good with conceptual stuff? All right, cool. I feel like we hit a lot of the big things right there. So now let's get into what we talked about on Friday. So nuclear chemistry, this will definitely be a decent portion of your quiz. On your ACS final, you can probably expect 4, maybe 5 problems to be nuclear chemistry. And in my mind, I think this is one of the easier things. So hopefully we'll talk about it here and you guys can agree with me on that. But there's not too many options of what they can throw at you with these problems. So this first one here is one of the half-life problems. We know that radioactive half-lives are independent of concentration. So they're basically going to be the same constant half-life forever. And so a good example you often see is carbon-14 isotopes as like carbon dating. That's a very popular process. It uses this. So here's a hard problem that I don't know. Has anyone done the practice quiz yet? Is this exact problem on the practice quiz? Okay. So this is a spoiler for your practice quiz. But okay, cool. A few years ago when I made this, or semesters ago, this was a problem that tripped a lot of people up. So hopefully we can talk about it here. But we have carbon-12 atoms. They're known to be stable, but carbon-14 atoms, again, that's an isotope, undergo radioactive decay with a half-life of 5,730 years. So the question is a little bit complicated, but it says if there are 4 carbon-12s and 4 carbon-14s mixed in a container, what species will be in the container after 11,460 years? So sit with this for a few minutes, see if you can figure out an answer. If you're a bit confused by it, don't worry, I'll go over it up here, but try to come up with an answer for this one. And then the little equation that I have here kind of represents what happens in the decay of that carbon-14. So if it goes through its half-life, we know that some of them are going to turn into nitrogen elements. And that's going to be beta decay or electron capture, I think. I'll start working on it up here. If you're still working on it, feel free to take your time. But the first way I would go about this problem is we're being asked to find something after 11,460 years. And we're told the half-life is 5,730. So I want to see how many half-lives take place across that time span. So easiest way to do that would be 11,460 divided by that half-life of 5,730. And that is going to equal 2. So that means we go through 2 half-lives across this time span. And then we kind of have to think about what amount of these carbon-14 atoms or isotopes is going to go through that half-life process. So the way I do this is I like to think about at the very beginning, we have 100% of that starting amount of carbon-14. Go through one half-life, that gets us 50%. And if we go through that second half-life, that means we're going to be left with 25% of the original carbon-14 isotopes. So then we have to think about what happens to the other 75%. Well, we already found out that when they go through their half-life, it forms that nitrogen stable element with 14. So the answer here is if we drew this initial thing with our 14 carbon 14, or sorry, our 4 carbon 14s and our 4 carbon 12s, after this amount of years, we'll be left with only one of those left, 25%, and the other 3 will become the nitrogen. And then we know that the 12 or the carbon 12 is going to stay the same. So this would be the answer. Does that make sense to everyone? I feel like this hits a few different things of like, how do we deal with half-lives? How do we deal with like beta decay, that sort of thing. So I think this is a good practice problem. Yeah, I can do that one more time. So if we were told that after the amount of half-lives, we have only 25% of that original isotope, that means that the other 75%, or for easy math, 3 of these 4, have to then go through their radioactive decay. And this is what we're told the radioactive decay looks like. When one of these carbon-14 isotopes goes through the radioactive decay, it turns into a nitrogen element. So that's what happens to those other 3. Is it okay? Okay. Next one. This is a problem you could expect to see tomorrow. Very standard. It's basically asking what happens when this isotope of bismuth goes through alpha decay. So this one does require that you pull out a periodic table. I wish I had one up here, but what is an alpha particle? What element is equivalent to an alpha particle? Helium. Yep. And we know helium, or the alpha particle, has a 4 as its atomic weight and a 2 as its atomic number. So if we have bismuth, 209, and again, that 209 is the atomic weight, undergoing alpha decay, that means that on the product side, we're going to be having an alpha particle and whatever's left over. So I kind of like the way that Dr. Blumman goes through these problems, where he's like, all right, if we have a 209 here, and we are putting 4 here, that means that it has to be 205 here. And then on the periodic table, bismuth is element 83. So I'll fill that in for you guys here. And if we have a 2 here, that means it has to be 2 plus something to be 83. So this has to be 81. And then all you do next is you go to the periodic table, see what element number 81 is, and it happens to be tellurium. So it looks like T alpha. So that's kind of how you do these problems. Again, I think these are not too bad. When I took the ACS exam, they do kind of, at least they did order it by unit. So it did coincide with like the end of the semester. So my last 4 or 5 problems on the test were kind of like this. And I thought that was nice. These are not too bad. Will anyone have any questions about that? Oops. All right, let's go back to electrochemistry for a little bit. I have 2 half reactions here. And again, oftentimes we're going to write these half reactions as a reduction. And we then compare the reduction potentials to see what's going to be reduced and what thing is going to get flipped and be oxidized. And this one, I'm asking to find the equilibrium constant K. So this does require we use a formula. I can write that formula for you guys. It should be E standard cell equals RT over NF ln of K. And I think you could use that abbreviation method where instead of doing RT and F, you do the 0.0592. I'm going to do it this way though, because on your ACS exam, I think it'll be written like this. But know that you can use that shortened method as well. So spend a few minutes working on this one. Here's the formula you have to use. And we're given these reduction potentials. So see if you can figure out what the overall standard cell potential would be. And if you're stuck, no worries. I'll go over it in a little bit. Let's work through this one. So first thing we have to do is find the standard cell potential. And what's the formula for that? Oops. Cathode minus anode. Come back, please. All right, cool. Cathode minus anode. Yep. So when we're finding the standard cell potential, and again, the standard is the one that has that not symbol on it, we do cathode minus anode, and that means we have to figure out what's going to be at the cathode and what's going to be at the anode. Because again, these are both written as reductions. So we need to figure out what is actually going to be oxidized instead of reduced. And anyone have a guess of these two? Which one is going to be at the anode and is going to be oxidized instead? Top one. Yeah, I was kind of giving it away there. So the way we do this is we compare what is the more positive value. And the more positive value is the one that is better at being reduced. And that's actually what's going to stay reduced. So if we have negative 1.66, that's less than negative 1.18, meaning that this thing that is less than is actually going to get flipped and become the anode. So cathode minus anode would look like this. This is at the cathode, minus, and we leave this minus in, so that overall it becomes now positive 0.48. And if you ever do this and you get a negative number for your standard cell potential, you did something wrong, because a very important component of voltaic cells is that they have to be spontaneous. And that means that this has to be a positive value for a voltaic cell. And that's the only type of cell that you guys are dealing with. Cool. So we have that. Now we can plug in our other values and we're looking for K. So in the problem, we're told it's at 25 degrees. So in Kelvin, 298.15. R is going to be the gas constant. That's the 8.3145 times 298.15 Kelvin. What would N be in this problem? 6. Yeah. So N is the moles of electrons that are transferred, and we have to always balance that. So again, we said that we're going to flip this aluminum thing to go the other way. And if we had a 3 over here and a 2 over here, the lowest common multiple is 6. Do we feel okay with that? That's kind of going back to last exam stuff. And then the Faraday's constant is 9,000 or 96,485. So we're going to put this into one big bracket. And this ends up being 4.28 times 10 to the negative 3. And if that's being multiplied by ln of k, then we're going to divide this on both sides. And then once we've done that, how do we get rid of ln? Base e. Yep. So we'll put this whole thing, the base e. We can base e cancel out the ln here. And so the final answer we're going to get is K equals 5.08 times 10 to the 48. Mhm.
Yeah.
Is it completely different?
Yeah. The math formula is 10 to the 21st. Yeah.
Okay, so that's like wildly different. Hmm. Let me try to think about why that could be. I've always used this one. Should it be? Mm. I would, well, okay. If you guys are all doing it that way, do it that way. I don't know why that would be a different answer. Maybe it has to do with the units of the gas constant,
That when it's like 25 degrees Celsius, right?
the abbreviated one. Yeah, and so this one should be okay. I don't know why it wouldn't be, but mm, I would do it your guys' way on the test tomorrow. Hopefully this doesn't screw you guys up. This should be the way it works, but if like you're getting a different answer, then maybe there's something wrong with my math up here. Like it's possible that this needs to be in kilojoules, but I don't think so. Um, so I don't know. So I use this one. Yeah, let me see. Yeah, that so this one should be okay. Like I'm looking at this right here, like this figure. Um, this is the one that I've always used, RT over NF. But if you guys on your formula sheet or what you've been doing up till this point is the other one, stick with that. I don't want to throw you off now. I'm not sure why it's different though. Oh, can I see the one that you used? Yeah. So I know you can use that abbreviated version for the like log Q one. Are you guys pretty sure you can also use it for the LMK one?
Logs. I've been trying to do it log.
Sure, if you want. We'll keep going, but like I know that the 0.0592 works for the one that looks like this, the E non-standard. Like I've seen this a lot, but so I would assume it also works for the LNK one, but honestly, okay, that's basically what I got. So that means that this one should be LN, the one that we did on that last problem.
But with the.
This is a different formula. This is the one where you're doing non-standard conditions and you're finding Q, not K. Okay. Would one of you guys mind looking for the formula sheet? Isn't it in Canvas somewhere? You got it up? Okay. Let me take a look at it.
It's the same one as that. The only thing is, yeah, doing for the log. Okay, I use the same one. But it's this one. But these two are in it's just right now.
Okay. So yeah, I was using this one then.
Oh, you're okay.
Yeah, I would.
Maybe it's because I know that when you said 293, maybe it's 295, much more than that. I don't even know.
It could have been if like the exponent was right.
Yeah.
It was a small number, like other difference, it was probably not a big deal. But to be safest, to use the formula that's given to you on the formula sheet. That's kind of what I would recommend. But we can move on because I don't want to confuse you anymore. And if you've been doing something up to this point and it gets you the right answer, then it'll get you the right answer tomorrow. All right. go back to radioactive stuff. So radioactive isotopes, we're saying that radon-222, which is an isotope, has a half-life of 3.82 days. And I'm giving you the initial amount of radon-222, and I'm asking what's going to remain after a certain period. So this one goes back to, I believe, the integrated rate laws that we did in Unit 2. You guys remember that? So there's first order, zero order, second order, all that stuff. So whenever we're talking about radioactive stuff, we're always using first order kinetics. And so those half-life, not the half-life, but the integrated rate law equations should be on your formula sheet still. And I think we're going to have to use one for this problem. So spend a few minutes seeing if you can figure this one out. I'll give you the integrated rate law for first order. It looks like this. Hopefully this is kind of ringing a bell. And then the first order half-life equation. And this one you might need to memorize. Looks like this. I think it's possible. Did he talk about this at all on Friday? Okay. Well, then maybe the bigger thing to be concerned about is remembering that this is the half-life equation for first order kinetics. I wouldn't say it's impossible though. He's talked about this in past semesters. If he hasn't talked about it for you guys this unit, probably you're off the hook, but we'll still go over this one because it's important. And if nothing else, you need to know it Thursday night. So it's a good review. Okay, so I'll kind of work through this one. If I saw this, I would probably go straight to integrated rate law, or at least I would try to do that. And I would see that we're given a starting concentration at 57.2. So I'm going to plug that in here. We're given a time. So they're asking after a certain amount of time. So I'll use that as well. 25.5 days. But then I don't have a K, and I also am looking for a final concentration. So we don't have every variable we need here. So that means we need to start with this half-life equation first. Because they gave us the half-life as 3.82 days. So we can use that to find K. Is this ringing a bell a little bit? Okay. That's ln of 2. Yeah, that's once you plug this into your calculator, that's what you get. And then so we'll multiply K on both sides, then we would divide by 3.82 on both sides. And we find that K is going to be equal to 0.1815. And now we have everything we need to solve for this last variable. So this whole right side of the equation is going to turn into negative 0.58169. And then again, we said to cancel out ln, we use the base e. So that's going to be the last step here. So then our final answer is going to be, we can write it like this. Concentration of radon 222 after these 25.5 days is 0.559 grams. Cool. Do we feel okay with that one? Hopefully some good review of integrated rate laws as well. This next one I think is a pretty good one. So I have a long list of, not that long, but I have a list of standard reduction potentials. So you might be given something like this tomorrow and you have to know what is going to be the strongest reducing agent or strongest oxidizing agent, that sort of thing. So as a quick review, remember that if something's reduced, is it the oxidizing agent or reducing agent? Yeah, the thing that's reduced is the oxidizing agent, and the thing that's oxidized is the reducing agent. I remember hating that when I took Chem 131 and 132. It seems annoying, but if you think about it, it does make a little bit of sense. The thing that is reduced is what allows another thing to be oxidized. So that's why it's called the oxidizing agent. I don't know why that took me so long to understand, but once I thought of it that way, it clicked. So we have this list where, again, all of these things are written out as being reduced, but we know that some of them are better at being reduced than others. So if I were to ask you point blank, what is the best thing here at being reduced, which one would we say? The last one, the most positive one. So that's silver plus going to form silver solid. So we could also say that the thing that would be best at being oxidized would be the zinc 2 plus and zinc. And if it was oxidized, we know we'd flip it and it would actually be zinc solid going to form zinc 2 plus. So we have that out of the way. Yep. So yeah, you got it. So the next step is talking about what would be the agents at play here. And so if we were asked to find what's the strongest reducing agent, we have to look at what's the thing that's best at being oxidized. And that's going to be zinc solid. Because we know zinc solid is really good at being oxidized to zinc 2 plus. And if we want, we can even write the oxidation potential as being positive 0.76 since we flipped it. So yeah, this would be the answer for the first one. This is the best reducing agent. And then what do we think the best oxidizing agent is? The last one, and specifically the reactant of that last one. So Ag plus is the answer. If it was like written, if they gave you silver solid and silver plus ions, that'd be kind of a tricky one, but the answer would actually be the thing that's in the reactant. So we would say this is the strongest oxidizing agent. Do we feel good with that stuff? Cool. All right. Only a couple more. This one, we're going to be using another formula, so hopefully we don't run into another dilemma with that stuff. But I've given you a redox reaction that's unbalanced, so we're going to have to balance it. That's going to be the first step we do. And that's not too hard. Don't worry, we're not doing the stuff from last unit. And I'm asking what would the value of the E cell non-standard be at 298 Kelvin? And then I've given you some concentration values. So I've told you that the iron ions are both at 0.02 molarity. And then chlorine, this might be tricky, but chlorine 2 is a gas. So that is going to be included in that Q or K. These are both 0.15 molarity. And then I've also given you some reduction potential. So we can do the cathode minus anode and all that stuff. So this one's pretty involved. This is doing a lot of different steps. So I'll give you guys a few minutes to work on this one. And the formula I used was this one. But use the formula that is like on your formula sheet. I think it's this one. And hopefully if you guys do the abbreviated version, you get the same answer as me. ln Q or log Q? Log, okay, I think you're right. One of them, when we do cathode minus anode, leave it as it is. And since they're both positive, the one that we subtract is gonna bring it down. But make sure that you're putting the things at the right spot. You know which one's cathode, you know which one's anode. So I've kind of gone ahead and balanced this one up here. So little bit tricky, but we have to remember to balance the atoms first. So there's 2 chlorine and it goes to form Cl minus. So we had to put a 2 here and we added 2 electrons to this side to balance that. And then the top one, we only added 1 electron, but we have to multiply the whole thing by 2. So the new equation would look like this. V2Fe 2 plus Cl2 goes to form 2 Cl minus plus 2 Fe 3 plus. And that does matter because when we go through and we do the whole Q, we need to make sure we're raising these things to their proper stoichiometric coefficient. So next step I would probably do here is figure out what is the standard cell potential, this part of the equation. So again, that's cathode minus anode. And the more positive thing is the thing that's going to get reduced instead of the cathode. So that to me looks like Cl2. So this is going to be at the cathode, meaning this is at the anode. So it's going to be 1.36 minus 0.77. And that should be 0.59 volts. So now we have this. And then the last part is going to be finding out what that Q is, and we can plug that in here. So Q should be chlorine minus squared, so 0.15 squared, and then Fe3 plus squared as well. So that's going to be 0.02 squared, and then over chlorine gas with no exponent times Fe2 plus, that's going to be squared as well. We're good with that part, products of reactants. Cool. So Q ends up being a nice number, 0.15, once you do all that math. So now we can set up the equation. E equals 0.59 minus, and then all in a big parentheses. I'm going to do it this way. Do it your guys' way. Again, I hope we get the same answer. R should be 8.314 times 298.15 over what is N in this problem? Not 6. What do we balance the electrons to be up here? 2. Yeah, this one is going to be 2. Because once we did this, we can cancel out the 2 electrons and the 2 electrons. He might give you a problem like that tomorrow, where it's like that simple. All you got to do is find N, and that would be a kind of easy one. And then again, Faraday's constant, 96,485 times log of 0.15. ln. This one has to be ln.
Yeah.
That sounds right. Yeah, since I did the whole thing. Maybe that was where some of the issues came on the last one. Okay, cool. That makes sense to me. Again, stick to the formula sheet. That won't steer you wrong. And then this whole thing, all of this over here, once we do this times ln of 0.15, should be, hopefully we get the same answer, 0.02437. We still have the 0.59. So then the E non-standard cell is going to be 0.614 volts. Anyone get that answer? 555. Anyone else get that? You got that? Okay.
It's got you abbreviated on this.
No, you should be able to on the exam. I don't want to say that. My work, when I did this in past semesters, I wasn't using the abbreviated form. And maybe there's a small difference with like the ln versus log or something, and that's what's causing us to get slightly different answers. If you're doing it the way where you do negative 0.0592 over n, and you guys are all getting the same answer, stick to that. I think that's probably your best bet. Cool. So, you know, 0.555. So, yeah, I don't want to confuse you guys a whole lot with this stuff. It's possible if the answer they're looking for is E cell, because you're not going to see an E cell that's like times 10 to the something. But if you're like on the last one solving for Q or K, he wouldn't give you like two very close answers, both times 10 to the 48, for instance. The exponent would be different in every answer, I imagine. But yeah, I hope I'm not confusing you guys more with this stuff. Stick to your guns with the way you've been doing it, the way he's taught you. It might be a little different now. But you're good. So I'll move on to the next one. Maybe later tonight, I'll go through and try these myself with that method, and I can like post a new answer key or something. Because I don't want to screw you guys over. All right, next one. This is, here we have a long list of reduction potentials, kind of in order of the lowest potential and the highest potential. And I'm asking which of the following could displace hydrogen gas out of acid? So I don't know if you would be kind of mean like I am on this problem and ask it in this confusing way, but let's look at what we got here. Because if I read this, I'm like, I have no idea what you're talking about. But displace hydrogen gas out of acid. This is the one where I see hydrogen. And we're producing H2, so that's hydrogen gas, out of H plus ions. Remember, hydronium ions or protons are acid. So this was a weird way of me asking, which of the following would let this stay written as it is, meaning that this would be reduced and the other thing would get oxidized. Does that make sense? Should I say that again in a better way? You need to find something that is worse at being reduced than hydrogen. So anything negative. Yep, that's it. So it kind of, this is a little similar to those problems where he's like, if you wanted to reduce the amount of rust that forms, how could you coat this in something? And when we were talking about that, reduce, the thing that gets reduced, let me start over. Rust is the thing that is oxidized. So when he was asking you those problems, he was asking, what is something that you can put over this metal so that it no longer is oxidized? Meaning make this thing get reduced instead. So this is kind of a tricky way of wording this, but basically, again, I'm asking which one allows that the H plus 2 electrons goes to form H2 gas. We know this is being reduced. How do we let this stay written as is? And that would be anything that is more likely to be oxidized. So if we go through the list, aluminum is a lot worse at being reduced. This one would get oxidized. So we'd flip that, meaning this is good. Aluminum is one of our answers. Zinc is also worse at being reduced than hydrogen. So zinc is going to be one of our answers. Silver is down here. Silver is better at being reduced, meaning that if we paired silver and H2, all of a sudden the H2 would be flipped and it would actually be oxidized like this, which would be bad. So silver doesn't work. And then gold is also down here. Gold is down here, and so it wouldn't work either. So the answer here is A and B.
So when it says displace, that means if that's what it is.
Displace, again, I worded this in a weird way. That means that we are creating hydrogen gas out of acid. Displace, placing. I don't like the way I worded that. He probably wouldn't give it to you like that.
But
yeah, displace hydrogen gas out of acid, meaning we're turning acid into hydrogen gas. So yeah, it's being reduced. Okay. Cool. Sorry about these couple problems with the formulas. I hope I didn't get in your guys' head about that. Stick to your guns, do what you've been doing on it, and that should get you there.